This presentation will cover heat pipes in an attempt to analyze and test their heat transfer mechanisms. Heat pipes take energy from one end and transfer it to the other through evaporation and condensation. A heat pipe transfers energy from a hot surface to a working fluid, which causes the fluid to evaporate. The vapor then travels along the pipe to the cooler end where it condenses, releasing the added energy. The condensate then is drawn back to its initial reservoir to be heated and vaporized again. Oftentimes, the internal pressure is reduced to increase the rate of evaporation at lower temperatures. Heat pipes have three main components: a vacuum-tight vessel, a small amount of working fluid, and a system to cycle the fluid such as a wick, centrifugal, or gravity-driven force. The most common heat pipes have a copper envelope with water as the working fluid. Steel and refrigerant are often used in energy recovery operations. Spacecraft often use aluminum and ammonia. Depending on the operating temperature and the amount of heat transfer needed, the envelope and working fluid can be changed to best suit each case. Due to the very high heat transfer coefficients for boiling and condensation, heat pipes are highly effective thermal conductors and are preferred over other heat transfer applications. Oftentimes, with electronics, fins are used as a primary heat transfer method. Sometimes situations require a greater measure of heat transfer, needing both fins and heat pipes. For experimentation, a copper and water heat pipe was built and tested to verify a mathematical model describing the heat transfer. You can see the heat pipe used in the experiment on the left. In order to control the internal pressure inside the heat pipe and be able to change the amount of working fluid, a simple ball valve was used. The end of the heat pipe was placed on a candle warmer, providing the heat needed to be transferred. To better control where most of the heat transfer was occurring, pipe insulation covered a majority of the pipe. During our tests, the thermal image on the right was taken and shows the areas of greatest heat radiation, verifying that most of the heat transfer is coming out the top end. The heat transfer through a heat pipe can be simplified and analyzed through a series of resistances and known temperatures. There is heat transfer directly from the hot surface to the cold surface through the wall of the copper tubing. That resistance is in parallel with the other three resistances. There is a convection resistance of the water as well as the vapor, provided that the Rayleigh number is high enough. There is a resistance for both the top and bottom cap of the tube that are identical, making them easy to combine. All the material properties for these resistances were easily found in tables, making the conduction resistances straightforward to find. The convection resistances needed a heat transfer coefficient, however. The type of problem used to find these values was free convection on a horizontal plate. After finding the Rayleigh number for both the water and vapor, it was found that two different Nusselt equations were needed based on the range of Rayleigh number. This Nusselt number led to the heat transfer coefficient, which was needed for the convection resistances. With the total resistance of the heat pipe and the temperatures at each end, it was possible to find the heat transfer rate. Simplifying the heat pipe came with several assumptions. The first assumption is that there was no radial heat transfer. This allowed for the heat to enter one end and leave the other end of the pipe. By doing this, it was only needed to take the temperatures at either end of the pipe. Another was that the pipe had uniform thickness when in fact there were joints where the thickness doubled. The assumption was also made that there was only air or only water vapor and never a mixture of the two. Because it was a sealed pipe, temperature measurements and pressures had to be estimated. Experiments showed that the best heat transfer occurred when the pipe was completely full of water, with the worst being when it had a small amount of water. In all reality, the best heat transfer would come from the pipe with the small amount of water, and the worst would be without any water whatsoever. After reviewing assumptions, looking at important factors, some explanations were found. Driving factors in heat transfer of heat pipes are pressure gradients and surface area. both of which were not heavily used in analysis. Pressure gradients occur from water expanding as it vaporizes and contracting as it condenses. This causes pressure differences at one end compared to the other, driving a mass flow rate. There are ways to analyze heat transfer with a mass flow rate, yet with a closed system it's hard to measure and know exactly what's going on inside. In an attempt to control the heat transfer to just the ends, the surface area that provides so much of the heat transfer was restricted. Leaving the insulation off the heat pipe would have provided better results, while making the equations needed much more complicated. While it is possible to do this evaluation, more sophisticated measurements would be needed to compensate for the non-uniform heat transfer patterns. This is evident in the fact that new research on heat pipes is being developed and explored even today. It is a complicated system and requires great care to analyze accurately. Ultimately, the complexity of how heat pipes function make them great at transferring heat and hard to accurately analyze. Thanks for listening.